Okay, so yeah, we stopped here last time, where we talked about topological surface operators and other related stuff. Let's see. There. Okay, cool. Okay, we'll now move on to the idea of quantization in this picture that we're developing. Oh, yeah. Quantization. Yeah. So different quantizations give rise to different interpretations of the path integral. Now we talked about the interpretations of like the correlation functions. The same correlation function can have different interpretations in terms of path integrals by performing rotations of the space, and that's how you get this conformal invariance, all of that from last time. So different spatial slices, so I think Kiran had the question about this, like how does time really come into the picture? So if you have to move from one spatial slice to another, what essentially causes this evolution between them? I said, oh, like time ordering comes in, etc. But it's essentially the Hamiltonian that causes the evolution. This is where, like what Pradyot said, the idea of the dynamical flavor comes in. But in Lorentz invariant theories, that is rotationally invariant theories, by the way, we are working under Euclidean signature. We can also consider evolving it after rotating this, right? So yeah, we have this, and yeah, I might try to do something here, but yeah, even after rotation, we can still calculate this time slices and path ordering. Let's say, for example, we have this one. After rotation, let's say the operator insertions are like this, and I can still calculate the time slices here, but it would look really different when I do it this way. Yeah, or something like this, or I think this can also be done, if I'm not wrong. Can it? Yeah.
Let me get all three points would be coinciding. All three points would be coinciding along the same time slice. So you will get a redundant system of equations. Like you won't be able to really distinguish the different points.
Exactly. Yeah. So yeah, you can also you have many ways of time ordering this essentially. So yeah, that's about that. So now the same correlation function gets interpreted as an expectation value of a time ordered product in some vacuum state. So what you essentially have is, you have theta 1, and that's inserted x1, and you have all these O's, and that is equal to 0 time ordered product of theta 1, t1, x1, and then you have tn comma xn. Okay, this is what I'm talking about. The evolution comes in here. So the underlying object is the same, but your right hand side, how we evolve, the time ordered product of in some vacuum state is different. That is, you have a different Hilbert space and time ordering. So essentially, you can, what this is saying is you can break up the path integral in different ways. That's basically it. suppose we have a bunch of operator insertions in our path integral, and at some time we insert p mu nu like this. I mean p mu, yeah. Because the operator is topological, it is the same as if we insert it at this time or even a later time, since we were talking about this picture. Yeah, it can be inserted here, doesn't matter, without crossing any operators. And we can neglect, we always write it as p news and the surface, right, sigma. We can neglect sigma altogether because of this reason. So yeah, this is actually the momentum operator, and this corresponds to symmetries. This is what we spoke about. Now, what happens if we move past an operator insertion? So this is actually violating conservation. So how does this get interpreted within quantization? So we have p nu. Now we actually need the surface. So let's say the operator insertion happens at some time t2 minus p mu of sigma. You can actually probably guess the form of this, but let me just write it out explicitly. Theta x. So this is the operator. This is the operator it's crossing. So that is this, right? The time ordered product of. Now, this is essentially your commutator that comes in here whenever you have like this crossing. And yeah, today is going to be a bit of calculation since we didn't do much last time, just to get used to the stuff, what we're doing essentially. Yeah. So because of time ordering, at T1, P should be first at T1, and then at T2, P should be last.
So when you write time ordered commutator of P and theta,
yeah.
Okay, so let's just take the commutator of P and theta, right? So that's P mu theta minus theta P mu, right?
Yes, yes.
So in each of these cases, is the P mu on the same time slice, or is it not on the same time slice?
It's not. They're two different.
Okay.
This is
okay, that's right. Okay, I see.
Yeah. If I understood your question correctly, yeah.
Yeah.
Okay.
And then P and theta just commute.
No.
Okay. Let's assume the P is on one time slice. I'm fixing a time slice, and just on that time slice, I'm computing the commutator P mu and theta.
Yeah, exactly.
In that case, it commutes.
Yes. Yeah.
Okay. All right. Cool.
Yeah. Okay. So yeah, we can then deform. Okay, we'll get to that point right now. So hopefully this clarifies your question. If I messed up in answering it, you have theta of x here, and let's say this was your p mu of sigma t1, and this is your p mu of sigma t2. This is after and before the insertion, right? So this is where the violation happens. This region, yeah. Now what you can probably do is, that's why you need the commutator here within the time ordered product.
What is theta exactly again?
Any operator. It's actually O, but I write it down as theta. Yeah. If that clarifies it. Yeah. So we can deform P mu of sigma T1 minus P mu of sigma T2 into essentially a single surface. Why can we do this? Because they're essentially topological operators. So we can do this, right? Yeah.
What are you doing? I'm kind of confused. You just
Yeah, we just inserting it at a different time slice without crossing the operator. So P mu just remains the same.
okay.
So we can bring both of these essentially here. And after
Wait,
that, what we can do, yeah.
Are we trying to like, okay, are we trying to establish some sort of like a limit kind of a scenario where
Yeah.
we can actually, instead of actually calculating the operator per se, we say that like P mu sigma T1 and P mu sigma T2, like both are approach this in a kind of symmetric manner towards the operator, and therefore we are able to map out how the operator is going to behave.
Yeah, very close to that. So what we can, well, actually, yeah, very close to that. So what we do is after we bring these two surfaces in closer, what we can essentially do asymptotically is we can surround this with just one surface. So it comes in and now it's just one surface. And this can be written down as, so let's consider the correlation function here. This is essentially a new surface. I'll call this sigma prime and theta. So just a correlation function between them.
This is the idea of like integrating around a contour, basically.
Yeah.
Okay.
So that's essentially.
So then the idea is like the operator that we are inserting is kind of like, so okay, the reason you said we can bring P1 and P at sigma T1 and sigma T2 closer to each other is because they're topological operators, the topology is the same.
Yep.
And theta and the operator that we insert is kind of like the offending topological term. Like it's the one that's violating, like it's not the same topology. Okay.
Yeah. Essentially, that's the thing. So
one second, I just have a geometric question here. I don't know if it's super naive, but anyways, so once we're talking about P mu, sigma 1, sigma T1 and sigma T2 coming together, we can establish only like, this kind of a boundary. However, to actually like, at least to form a closed surface, it makes sense if you need another set of operators or another set of like another time slice which is orthogonal, or at least like distinct from this time slice,
right?
Yes. I mean, which is distinct from this time slice in order to form a closed distance. So I'm thinking maybe you should...
that's why I use the word asymptotically, right? You bring it close asymptotically to form the closed surface.
Okay.
It's like in the limit.
Okay.
Let's just think about it, right? Like say you're far away from theta, right? Like you can bring the two of them and make them touch, right? But it's just in the neighborhood of theta that they can't touch. So like you have both of them becoming one line, they split near theta, region after theta, and then far away they again can become one line. So that because like technically you can bring them closer far away, you can isolate some bit that looks like a circle and then you just shrink the circle around theta.
So we are essentially establishing, or like you're essentially bringing in some sort of a symmetry because of the asymptotic condition.
It's not exactly symmetry.
You're assuming some sort of.
You'll see what I'm trying to do with the next line. So here on this equation, right here, we can use the word identity. This will essentially then equal, just a second. Yeah, if I get this right. Yeah, so what this will in the end give you is because of what we'd done previously. We have our first equation of this algebra. And everything is going to work out in a similar way. This is why I wanted to do this. This is why I wanted to bring it into a single surface.
So if you can increase or if you can decrease the thickness of the surface to arbitrarily small scale, still it just basically the point. Why are we even looking at the surface instead of just talking about it as a point?
Yeah, so it's still on a surface. This is a surface operator, and that is because of this part.
Okay. So that, okay.
Yeah. So just a second.
I have like a lot of like geometric and
questions.
At the same time,
we can actually clarify this. And that can be our detour probably whenever we talk about conformal bootstrap next, because and we're also going to talk about how like criticality comes in with the icing model, water, all of this stuff. Yeah, but we'll move on for now. For the sake of completion. So now you have this previous equation, a different, but here if you notice, a different direction of time, right? Like a different interpretation of path integral actually leads to the same equation, if you think about it, because we are essentially surrounding it in the end. So yeah, it shouldn't make a difference. So this is also independent of interpretation, like the correlation function. Yeah. Right. So now we have the previous integration, which equation once integrated gives you something of the form of 0 of e to the power ipx. This is the evolution part. And this is true in any QFT. But
shouldn't one of them be minus IPX?
Oh, I'm sorry. You're right. That's about it in this case. But if you've actually noticed, I've just rotated the space, but I haven't brought any ideas of conformal invariance in it yet. So in fact, none of this has been conformal until now. So conformal gives us more symmetry, and that is what gives us more power to deal with these QFTs in the end. So let's bring in the conformal symmetries. So using conformality. That's a word. Yeah. So using conformality. Now, let's say there is some vector field, epsilon, which is epsilon mu, mu. If the notation seems confusing, excuse me on that. So let's say there is some associated charge with the surface sigma, right, on this vector field. So you have epsilon, sigma. ds mu epsilon mu t mu. Yeah, that should be right. Where this is your current, right? So if this charge is essentially conserved, what do you have? You have first that your current, divergence of the current is 0, right? Yeah, I'll just ignore the indices for now. Actually, if I got the right index here.
Minus, okay. Oh, okay.
Yeah. So here, first it acts on epsilon, and then it acts on T mu nu, right? But we know that divergence of T mu nu is 0 for our QFT, local QFT. So what you essentially have is plus 0 equals 0, right? And this is, so since T mu nu is symmetric, this can be written down as dou mu epsilon nu plus dou nu epsilon mu T mu nu equals 0. Yeah. So that means this part has to equal 0. So do you guys recognize this from somewhere? All of you are on mute, by the way. Yeah.
E nu, it's okay. This kind of looks like how you define your F mu nu.
Yeah.
Using
It is
like, oh, okay, of course. Right. In a more general sense, it would be a killing vector.
It's a killing vector, but yeah, you're kind of right. So one of the solutions.
1 second, go. 1 second, go a little up. Okay.
Wait, so stupid question, and this is getting completely off track now at this point. So
Yeah,
then,
that's fine.
is what we like in traditional QFT when we do the gauging and gauge fields? Is that like? Well, that's not a killing vector, is it? It's not. It's something very different from that.
Yeah, viewed in the right context, maybe it's different. Oh, what we do there. Yeah.
Right. Okay. All right. Okay. Now back.
Yeah. Okay. I mean, can it be? Let me think about that. I think it can in the right context, right?
Now that I feel like, okay, so here's the thing. There was this idea of doing like QFT in curved spacetime, and that went completely downhill. And one of the motivations for that is like there's so much similarity between the geometry of general relativity and the geometry of gauge fields.
Yeah.
But like somehow they don't mesh well together. So, I mean, like what we end up talking about the gauge field, that's kind of analogous. Like we use that to define a covariant derivative. So AMU is kind of like your connection in GR, right? And then like there's a lot of other messy things I show. But like I don't think that is exactly I don't think we can refer to it as the killing vector.
Yeah. I'm just saying. So you have the lead derivative of let's say there's a vector field X and you have a lead derivative that vanishes with respect to a metric G. In local coordinates, this amounts to a killing equation. So in that sense, you can bring it in, yeah, the killing vectors into like when you're considering lead derivatives, that is. So let's, and your question was in electromagnetism, right? Essentially. Yeah. Yeah, I think we can bring it in. Yeah.
Let's get back to it.
But yeah, that's actually a good question. Anyway, yeah. Let me get back to this. Give me a second. Yeah. Okay. So one of the solutions to this killing equation would be, let's see. I think it is this. Correct me if I'm wrong. This is your P mu, that is your I dou mu. Yeah, and which this is as you can see, a generator of translation. And you also have another solution to this. You can maybe guess what this is. Pretty simple. This is your rotation. Okay.
Wait. So mass, if I understood it right, okay, so the momentum becomes your some sort of a like a complexified derivative, and therefore your mass is like
this is not mass, by the way. This is just you use m to denote rotations.
Okay.
Yeah,
okay.
No connection to
Pull
mass.
Could you just go up a little bit to the killing equation? Yeah, that's all.
Mass is a scalar. It shouldn't have mu. I was
How
confused.
how does PBU satisfy that definition? Because like it looks like that'll just be 2I. Oh, because you end up taking the divergence of. Okay, I see.
Exactly. Yeah.
That's clever.
So,
that's really clever.
Yeah. So yeah, these are two solutions, right? And we haven't still brought in any conformal stuff. But now, what is the defining feature of conformal field theories with regard to the stress energy tensor? It is that
once.
Yeah.
Have we okay? What exactly is the interpretation of P mu is equal to ID?
I don't know. That's just your momentum.
P mu, like what is that?
That's your momentum.
What translation
that's just the
is that?
No, that's just momentum operator in quantum mechanics.
Yeah, that's your momentum operator in quantum mechanics. That's it. Right?
Okay. Cool.
Yeah.
Right.
In more recognizable terms, minus IH bar
delta.
Yeah, d by dx or something like that.
Yeah.
It's the same thing. I've just dropped constants and done a lot of stuff. Okay.
No, here again, the fact that there is no dt is what keeps it all together.
Yeah. Okay. Yeah, exactly. We're just viewing it like a dynamical theory. Yeah. And now you have your stress tensor for the conformal field theories. Now, what is the defining factor? Is that it is traceless. And this is again another operator equation. Remember we spoke about operator equations last time, and that it should not interact with any other insertions, all of that. Same things hold here. Yeah, this holds when it's inserted away from other operators. We are not going to do word identity here explicitly for now, but you can do it, and it will come to use probably in the third session of what we do here, or maybe even later. So this implies that the theory is insensitive to changes in the metric, right? That is, it's proportional to the metric. So if your changes are proportional to the metric, it is insensitive to it, the stress tensor.
Could you just briefly run through this argument, because I don't think I've seen this before?
Oh, okay. It's very simple. So you get this part, right? Why conformal field theories have the trace 0. Okay. So once you have this, now you do any operations with the metric here. So what I just told you about, This killing vector is killing vector is essentially related to the Lie derivative vanishing, right, under a particular metric. So everything hinges on that metric. And when you have the trace going to 0, your metric, like if it's multiplied proportionally, it's just it's just the dilation of the metric or a contraction, whatever.
Or it's just like okay, we don't care about rescaling the metric.
Yeah, no, it is. What do you mean? It's just a dilation. It's just proportional to the metric. Hope that's clear. Yeah.
Oh, and is that, sorry, just a quick thing. So is that also because, like, in a conformal field theory, we don't really care about distances, we care about the angles. So is that one of the reasons we really don't care about if the metric gets dilated or something, because the angles still stay the same?
This that wouldn't be the cause, that would be the effect of it.
Okay, I see.
In mathematical terms, like it's the trace of the stress tensor. You can think about like why that happens essentially, or we could talk about it probably after the call,
sure,
or something like that. So for conserved charges, we can actually relax the condition a bit in terms of the killing equation. So what we can do is we can say that this doesn't have to necessarily be 0, but has to be a multiple of the metric. This is known as the conformal killing equation. So taking the trace of both sides with the metric, we can figure out what CFX is. This actually leads to some extra solutions to the equation on top of rotations and translations. Notice that they still work here, trivially. So now,
do the extra solutions have something to do with like some sort of a charge or something coming in?
Yeah. All these are like for conserved charges, right? If the charges have to be conserved, this has to be a solution to the killing equation. So this is known as dilation, or apparently people call it dilatations. I don't know why. Yeah, but dilations make more sense. This can be thought of as rescaling of X, right? And you have something known as special conformal transformations, which is of this form. X nu dou nu, minus X square dou mu.
Is this the one where the origin is at the center, and then you have like X and Y axis are like loci circles around like
that's exactly
on top
this.
and then
That's this. You're right. So it's a good exercise to verify these equations hold true as solutions. In 2 dimensions, there are an infinite number of solutions leading to an infinite number of conserved charges. And that's why 2D CFT is big, because of the freedom it allows in this sense.
So for these extra solutions, all you've done is throw in an X nu.
Yeah, you can say that.
For both for your momentum operator and your rotations.
Yeah, essentially. So your K mu is actually called an inversion, where your X mu becomes X mu over X square. So what, as Pradyot said, it takes all the points outside a sphere and maps it into a sphere, and takes all the points inside a sphere and maps it out of the sphere.
This is insane.
Yeah, and
This is absolutely crazy.
Yeah, so it's essentially, so whenever we do transformations, we are actually fixing origin. This can be thought of as fixing infinity and then going ahead with translation, and by moving the origin itself, which is a very interesting idea. So we have the necessary background to establish conformal algebra.
Okay. Oh, 1 second.
So the
I
origin.
think.
Okay, sorry.
Go ahead.
Yeah.
Go ahead.
Go ahead.
Okay, fine. So basically, the origin is going to like another set of like far off point at infinity, but at the end of the day, it's like throughout. Is that what is happening?
To get a geometric intuition for this is hard, but I guess it works.
Like all the points at like infinite distance, since infinity is like, what's the word for it? It doesn't care where it is. It doesn't matter if the infinity is there or here or there. Like all the points on that
like that,
far off this
but
thing,
now it's
they're
the
all
origin.
origin. They're all mapped to the origin. It's
exactly.
pretty fascinating.
Yeah.
Yeah.
Okay.
Okay. So what I wanted to like bring in was like essentially I think Penrose was trying to work on this. I forget the name, but essentially it is study like it's basically when you're looking at QFT instead of instead of looking at it in normal space time, you're looking at it from a point of view of a light or like a photon. So what happens is, what was the last thing that he was working on, which was extremely famous? Like
his own version of Felicity or something like that.
No. Anyway, so in that, so what happens is you do some sort of a projection inversion, like what you're doing here. So that immediately
He's
like
working with twistors or something. Are they? Is that what it's called? Twistors or something? You have like you have Witten's twistors.
Yeah, he's working on twistors. Penrose was one of the very first few people to actually go ahead with twistors, and you can do a lot of crazy stuff with it apparently, but it's just the maths has all gone over.
But is that what you're talking about, Pradyut?
Okay.
Is that what you're talking about?
I don't think so. Anyway, we can come back to this later.
Okay, we'll come back to
this. If we remember the name, we'll come back to it later.
Just for the sake of throwing out names of things I know is done, there's something called either spin forms or spin networks or something like that. Is that what you're talking about?
I don't think so. It's something different he's talking about. Once you get to remember the name, maybe we can clarify on the idea. Yeah, anyway. So coming back to this, so first you have the commutator of two charges is equal to commutator of the charge on the commutator of the fields. So this is essentially violated in some cases, for example 2D, and this is due to projective representations of the normal group instead of just the group representations. So in path integral language, this tells us how to move tells us how to move the commutator. That is, or rather, it tells us how to move the topological surface operators past each other. So, for example, we have this these are rotations, by the way. Yeah. And this is essentially the algebra of SO in D dimensions, whatever. Yeah. Then you have M mu nu P rho equal to I to mu rho P mu minus tau mu rho P nu. Okay. This just says the vector P is a vector under SOD. Okay. Similarly, you have the same thing for K rho. It's essentially the same relation if you want to write it out. There are also other commutators where you have D P mu. Yes, I P mu. These actually you might have come across a version of these things in while doing QM, but yeah, like basic QM. K mu minus I K mu.
What is D?
Your D, I guess the eigenvalues of D is essentially something called the dimension.
Okay.
That is the operator. We'll get to that as well. Yeah. Then you have P nu minus 2I. Yeah, the delta rho mu nu. Just a second. I mean, whatever. Minus M mu nu. Yeah. Okay. Yeah, as I said, we'll see what D is. But the eigenvalues of D are of the form of I delta, where delta is greater than or equal to 0. And this is essentially called the dimension. Yeah. And P mu and yeah.
Is this like some sort of scaling?
Can you consider it a scaling? I don't know if you can.
Okay.
Yeah. Yeah. So here P mu and K mu act as raising and lowering operators. Actually, yeah, you can actually consider it as scaling. Yeah, never mind. Yeah. Yeah, you can actually consider all these as scalings of dimensions, because your P mu's, they're yeah, let's see. Yeah, the eigenvalue that appears to the right of the commutators, right? P mu always acts as a raising operator. So +1 would be the value it gives out. D and mu, it's like 0. And K mu is like -1. So if you observe here, K mu and we have K mu and P nu, and their commutator is essentially something equivalent to being 0, like a 0 dimension thing. Yeah, we'll talk more about dimensions soon. Yeah, okay. Let's see. Okay, I think this is a good place to stop for today. Next time, whenever we have it, we'll talk about something called primaries and descendants. This is essentially a way to classify operators in the theories according to symmetries. Yeah, that's where we'll go ahead with this. But
also,
yeah,
just remember, like the Penrose, it was twistor theory.
Yeah, it was twistor theory, right? Yeah,
Yeah.
that's what I thought. So yeah,
I forgot the name
Yeah.
for some reason, but essentially it is when we talked about invariance and some sort of this thing coming in, right? So I think so. I had a very hard time like understanding what that inversion is all about, like at least physically, because it doesn't make any sense. Like how will
Yeah.
the x-axis just convert it to? I mean,
Yeah.
look, and all that kind of stuff. But essentially, what I think it is like you can probably like uh, I don't know. It's like I think it's very deeply connected to twister theory because in twister theory you have like instead of looking at normal space time and then translation like time like and space like translations and all that, you just consider everything from the point of view of a photon, which means certain like there are a lot more symmetries established. So
Can you speak about this next week then? It'll be interesting to go into this.
sure.
Okay,
I mean,
I'll
I have
just
to
stop
see.
the recording. Yeah.
Yeah. Sure.